stream of Physics 232. This is week 9. Today we're talking about fluids. We're going to go over Pascal's Principle. We're going to go hydrostatic force, that is, and osmotic pressure, and other fun things like that. I'm going to do a few bookkeeping things first. First, we're going to post a couple links to the Learning Center's website, Facebook, and Instagram in the chat here. So definitely check out the resources they have there, or look them up on Facebook, Instagram, and follow them so you can get updates to new resources the Learning Center has. I'm also going to paste in there an attendance sheet, which is just a quick Google form you fill out, let your teacher know that you've been here. There's that. And we can get started here. So let's start by talking a little bit about just fluids in general. So fluids, we like to think of fluids as liquids, and like water is a good example of a fluid, but air also counts as a fluid, or any gas. So fluids can be any gas or liquid. They both kind of behave in this fluid manner. And when we're talking about fluids, a lot of times we talk about density. So density is equal to the mass over volume. So mass divided by volume. The units for those are usually kilograms per meters cubed. Density is usually signified by this Greek letter rho. It looks like a P. I usually draw it with a little tail on it. Oftentimes you'll see it, it's kind of at a slant, and then a P, something to that effect. But this is rho, which is the Greek letter. I like to differentiate it with that tail so I don't confuse it with pressure or other types of P variables that we use. So, and pressure is another thing, the big capital P, which is equal to the perpendicular force and I often will see it as the force with a little perpendicular sign next to it, divided by the surface area that force is being applied on. So it's usually that force is distributed over a certain area, and so we look at the force per area of it. You can see the difference in force. If like you were to poke yourself on the arm, you could feel that pressure. You could apply that same force but at a much wider area by using your palm, and you wouldn't feel as much pressure on your arm. Similarly, that same force on a little needle, if you're getting a syringe or a vaccine if you're lucky, and it'll poke right through your skin, and you'd barely feel a prick at all because it'll pierce through even though you're not using that much more force. It's just the area has shrank down, so the pressure is much higher on that one point. We can move on to the idea of Pascal's principle. Where we really have the change in pressure is kind of constant and this is usually dealing with like a hydraulic system or something to that effect. So I'll say this is a constant. And this lets us say, therefore, if we were to have like a 2-tub system, I'm going to draw 2 tanks. One tank is kind of wider, the other tank is much more narrow. And we draw a little channel connecting them there at the bottom. Excuse me. The pressure in each of those is going to be the same, and we could have some liquid in there. So the height of that liquid is going to be equal. We could apply then a force. Let's apply a force in red. If we applied a force on a piston that was sitting across that, and we pushed down on that, it would apply a certain force, and it would move and displace a certain amount of water here. Just a little bit. If we just moved it down just a little bit, the amount of water displaced would be much higher over here, just because the surface area is different. So that change in height for the two waters is relative to the change in surface area. But really the volume of that water is going to be equal in each of those things. And we can see that So the pressure here, which is the force per area, that's the pressure in, is going to equal the pressure out. So we can say that the force in divided by the area in is going to be equal to the force out divided by the area out. And this is the nature of how hydraulic systems work. How you can push down on something and you can lift up a car or something really heavy because they distribute that weight over this big area. And you end up having to push a much farther distance so you can lift up that car just a couple inches, but you don't have to put a lot of force into doing it because the work on either side of that's the same. The force times distance on there is going to be the same idea, or the pressure times distance is the same on each one. So let's get an example. And here we have a hydraulic lift, and this is kind of a better drawing of what I just kind of tried to draw there. And we have a simple piston, so there's a piston in here, this area and this area. It's kind of blocking, containing that fluid. And remember, most fluids are not compressible. Some of them are, but most of them, they compress very little, which is why this is allowed to work, where the force pushing up is more air. Air is very compressible. We can condense air a lot easier than we can liquids. So here we have a hydraulic lift, and it has a small piston with a surface area AN of 0.45 meters squared, and a large piston with a surface A out. So this is the area out. This is the area in. With the area out is equal to 3 square meters. And we're applying a force of 18 newtons going down into that small area there. The question then is, what force will the large piston provide if the small piston in a hydraulic lift is moved down as in the figure shown? Well, just like we were saying, that pressure in needs to equal the pressure out. And to get equal pressures, we can set the force in divided by the area in needs to equal the force out divided by the area out. And now we just need to solve for what force will the large piston provide. So the force out, the large piston. So solving that for force out, I get force in divided by the area in all times the area out. Just multiplying each side by the area out. This gives us the value of the force out. So we know that the force in, I'll write it in green, force in is equal to 18 newtons. The area in is equal to 0.45 meters squared, and the area out, they said, was 3 meters squared. Did I get that right? Yes, I did. So plugging those values into there, we get 18 newtons being the force in divided by 0.045 meters squared. That's the area in. Then that whole thing times the area out, which was 3 meters squared. Oops. Let's go here, and we're going to take 18 newtons. We're going to multiply that by 3 meters squared, and we're going to divide the whole thing by 0.045 meters squared. That's 1,200 newtons of force is what we're getting. 1,200 newtons. So this is a great example of how The work is the same on each of these, but we're only pushing down with 18 newtons, and we're getting 1,200 newtons of force going up. So I can push down with 18 newtons pretty easily, but I can't lift up a car, and 1,200 newtons would probably lift up a car. Or they use hydraulic lifts a lot when they're lifting up these automotive cars. They have a small motor working in a hydraulic system, so they can use a little bit of energy or a little bit of force to push things up. It would be the same amount of energy either way. We're just doing it for a much longer time period. Now, you might ask yourself, well, how far do I actually have to push down on there? So, if the small piston is depressed by a distance, dy in inches or in is equal to 2.4 meters, and there's no friction, how much will that large piston rise? So now I'm actually pushing down on 2.4 meters. That's a little bit taller than I am. So you have to 18 newtons push down the height of me plus a little bit. And we have to see how high up that 1,200 newtons is going to lift. So, like I said, the work going in has to equal the work going out. The work in needs to equal the work out. So that means that the force in times the distance in needs to equal the force out times the distance out. So we want to solve for the distance out, right? How much will that large piston rise? Dividing each side by the force out, we have the force in times the distance in divided by the force out needs to equal the distance out. So we can solve that because we know the force in is equal to 18 newtons. So that's 18 newtons. We know the distance in they give us here now is 2.4 meters. And we need to divide by that force out that we calculated from the first part. That's 1,200 newtons. And that should tell us then the distance. So that would be 18 newtons times 2.4 meters divided by 1,200 newtons is 0.036 meters. And that's equal to your change in y of the large piston, how far it moves up. So that's kind of how hydraulics work and why we're able to push things up. You notice we push down a little taller than I am. I said 2.4 meters, and we're only getting 0.036 meters up. So we're only lifting up just a tiny little bit. So these hydraulic systems, they have to push down on something, but they have to push down on a really long thing so they can get a little bit up. Here's a fun problem. Here we have this cylinder, which is suspended in a solution, a liquid solution. And it's in a depth where it's actually stable and at equilibrium, which means that the forces going up are going to equal the forces coming down on it. The pressure of the liquid is kind of all around it. And Pascal's principle says that the change in pressure is going to be constant for everything. Now, we should note, we want to prove that the buoyant force of the cylinder is equal to the weight of the fluid displaced in this case. And we can assume that the buoyant force is the force 2, which is the force down here at the bottom, and minus force 1, which is the force on top. And that the ends of the cylinder have equal areas. That just makes our calculations a little bit easier. So really, the Archimedes principle says that the buoyant force is going to be equal to the volume of the water that's been displaced by an object that's suspended in it. And we can prove that here. So if we were to take those forces, we say that force 2 minus force 1 is going to be equal to the density of 2 times the area. In this case, the area is the same, just here and here. They're both equal to each other, minus the density at point 1. So the density at the top and the density at the bottom, times the area. Now we can factor out that area because they're common, and we can say that density A minus, or I'm factoring out the A, minus density 2, 1. So the density of 2 minus the density of 1 factored out times A. That's going to be equal. We're just plugging in the values for density, really. I guess maybe that's pressure, because that pressure is going to equal H density of the fluid times the gravity. Pressure times area is, yep, that should have been pressure. My mistake. I always screw up my P's. And this is pressure 2 minus pressure 1. Pressure 2 minus pressure 1. So now, remember that pressure is equal to the density times the height times the area of something. It's kind of the pressure. So it's really force times height, or force divided by the meter squared, the surface area. So we multiply by that surface area, we get the force, and the pressure is just going to be mass divided by volume. So multiplying by the height, we get mass divided by area as well. We should be able to, this is not, my brain. This is gravity, not area. That's why it was screwing me up. So yeah, again, let me break this down so I can actually make sense here. P is equal to mass over volume times H times gravity. H is just one dimension of the volume, so this is going to be equal to mass times gravity divided by volume, or 1 over volume times the H is just going to be equal to the area. So that's how we equal pressure. So here I'm factoring out, I'm going to substitute this value here in for pressure. So that's going to be the height at 2, the density of the fluid, which is going to be constant throughout the whole thing, times gravity, minus the height at 1, the density of the fluid, times gravity. And we're still multiplying by the area. We can factor out these common factors, the density and the gravity. So that's equal to H2 minus H1 FL gravity area. So the density times gravity times the area, just multiplied by the change in height. Like I said earlier, the change in height times the area is going to be equal to the volume. So this is actually going to be equal to the volume of the fluid. Up here we were talking about the cylinder inside. Now we're talking about the fluid around it. So the volume of that fluid times the pressure, FL, times gravity. Or sorry, not the pressure, the density of the fluid times gravity, which is equal to the mass of that fluid times gravity, which is equal to the weight of the fluid. So that's kind of a proof of Pascal's principle, where the force going on top and bottom is equal to the volume of the water that's been displaced. So if you were to suspend any rock or object inside water, as long as it's submerged in the water, the buoyant force pushing up on that object is equal to the volume of the water times the density of its water times gravity, which is really this equation. The volume of the object, water that's been displaced, times density times gravity. So let's talk about osmotic pressure now. So osmotic pressure is, you have these two volumes, in this case, one on the left and one on the right. And the one on the right has a solution in there. So there's some particulates that's dissolved in that solution. One on the left is a pure solvent. So this is kind of like pure water, with this one over here could be kind of salt water. That's a good way that they've used osmotic pressure. And you have these separated by this small tube with a semi-permeable membrane. So what that really is there's just a small membrane with tiny holes in there. And the holes are small enough to keep the salt out, the larger solute particle, but it does allow the water or the solution to flow from one side to the other. And you can look on the right-hand side. This is kind of the idea of how they would use it. You could pour salt water in this side, and the pressure difference between here, they want to be at equal pressures, because you still have one atmosphere pushing down on both of them, but when you get down to here, the pressure of all the water above it is greater. So this is at pressurized, and it's pushing the water this way. So here you get the pure water, and the salt water stays up here. And so we can use that, and they would eventually equalize in pressure. And you could drain water out of this, so this would continue to push through. You could put more salt water in there. You could let it precipitate out. You could scrape out the salt water. So there's lots of ways we could use that to desalinate water. It does take pressure to kind of push down on that top part, and you could even pressurize this top part of it here to add more pressure to force that water through at greater speeds. But we can calculate the osmotic pressure using, here's a symbol. It's kind of a capital pi, just to be fun. That stands for osmotic pressure. And that capital pi, osmotic pressure, I have to do a straight bar, is equal to the density times gravity times the height. Excuse me. So that's the height of the solution. And we have a law that says Van 't Hoff's law, which, sorry about that. Van 't Hoff's law lets us calculate the osmotic pressure based off of the concentration of the solution times R times T. So the concentration is going to be equal to the moles per liter of the solution that we're trying to filter out. And the R is going to be a constant, which is equal to 8.206 times 10 to the negative 2. The units for that is liters times atmosphere per mole Kelvin. That's just a constant value. We use it in the ideal gas law as well. It's really useful in chemistry. The temperature is going to be our temperature in Kelvin. And we can use this value then, knowing the concentration of the solution, the R, and the temperature, to solve for osmotic pressure. So we're going to have a multi-step problem here, where here we have a patient that has suffered blood loss, and the healthcare provider is providing a saline solution for injection. The osmotic pressure of the blood cells are 7.5 atmospheres, and the prepared solution should be isotonic with those cells. To prepare the saline solution, how many moles of N solute should be put into a 1.5 liter of distilled water? So that's what saline solution is, right? Just salt water. So we know, based on this, that the osmotic pressure is equal to 7.15 atmospheres. The temperature of the body is about 37.15 degrees C, which is equal to 310.3 Kelvin. Remember, the conversion between Celsius and Kelvin is whatever your temperature is in Kelvin, we just add 273.15. Yeah. Which is equal to our temperature in Kelvin. The volume that we're talking about here, V, that's given in the problem, 1.5 liters. And then we have our value R. I'll rewrite again. It's 8.206 times 10 to the negative 2 liters times atmosphere Kelvin times mole. And we're trying to find out how many moles that we need to use. So using Van der Waals, or we can go back and use kind of this idea here. Well, that's pi, or the osmotic pressure is equal to the concentration times R times T. And remember, the concentration is really the number of moles per volume times RT. This is osmotic pressure. So we have the volume, we have the R constant, we have the temperature, and we have the osmotic pressure. We want to solve for moles. So by rearranging this equation to solve for moles, we have N is equal to the osmotic pressure times V divided by RT. We can then plug in those values. So plugging in N is equal to 7.15 atmosphere times 1.5 liter divided by our R constant, 8.206 times 10 to the negative 2 L times atmosphere divided by K times mole, moles Kelvin. And then we're going to multiply that by our temperature, which was 310.3 Kelvin. Notice unit-wise, the kelvins are going to cancel out there. The atmospheres are going to cancel out there. And the liters are going to cancel out there. The moles are in the denominator of the denominator, so they're going to flip up to the top, and our answer is going to be in moles. So let's plug that into our calculator and see what we get. 1.15 atmosphere. And we're going to multiply that by 1.5 liter. We're going to divide that whole thing by, I said 8.206 times 10 to the negative 2. Units on that are liters times atmosphere divided by, let's get the temperature in Kelvin. Don't ask me why this puts a degree on Kelvin, but we'll take it per mole. And we have to multiply that now on the bottom by 310.3 Kelvin. And that's 0.421196 mole. So let's go to 0.4212 moles. 0.4212 moles. So that's how we have to find how many moles of solution that we need to add to 1.5 distilled liters of distilled water, so we get that same osmotic pressure that's in our bloodstream. And you can, once you have the moles, you can use the molar weight of your salt that you're using, usually sodium chloride, to convert that into grams, so you can actually have a value you measure out as well. Mistakenly, the concentration of the solution is only a quarter of what it should be. What would the net osmotic pressure exerted on the walls of the red blood cells be? So we expected, if we did everything correctly, the moles to be 0.4212. That's what we just solved for in this last problem, part A. In actuality, we really had a quarter N, which is equal to just dividing that value by 4. Let's do that real quick. 0.1053 moles. 0.1053 moles. Now, we know the osmotic pressure of the bloodstream is equal to 7.15 atmospheres. We know the temperature of the body, still equal to 310.3 Kelvin. Just rewriting it because it's all on the last page. I know that R is equal to 8.206 times 10 to the negative 2 units. Basically are to cancel everything else out and get the units we want in there. So that's liters times atmosphere per Kelvin per mole. And we want to find the net osmotic pressure. So that's the osmotic pressure of the blood minus the osmotic pressure of the solution that we've mistakenly measured or mixed together. So that's osmotic pressure of the blood minus the osmotic pressure of solution is going to equal that 7.15 atmosphere minus, and now we need to subtract from that the actual moles that we have. So that's 0.1053 mole. We're going to multiply that by R. Let's just write RT. We're going to divide that by V, because the actual moles that we end up mixing into that solution divided by V, that's going to equal our concentration of the solution times the R times T gives us the osmotic pressure of that solution. So now we have the same units for that. We're going to plug in those values. Notice the volume R and T are not changing. The only thing that's changing there is N in this case. So I'm going to go ahead and plug that in here. First, I'm going to solve for the osmotic pressure of the solution. So that would be 0.1053. I just had it up there. Let's use that. This guy times, and I had 8.206 times 10 to the negative 2. Units were liters, atmospheres divided by Kelvin times mole. So that's R. Now T was 310.3 Kelvin. And we want to divide that whole thing by our volume. Oops, wrong value. And that was 1.5 liters. And this is giving us an answer in Pascal. We actually want that in atmospheres. So let me just tell it what I want. And it's 1.7875 atmospheres. That's the pressure, the osmotic pressure of the solution. So 7.15 atmospheres minus, this is going to be osmotic pressure, the net osmotic pressure, is the osmotic pressure of the blood, 7.15 atmospheres, minus the, I forgot what I just said, 1.7875, 1.7875 atmosphere. Let's see what that equals. 7.15 ATM minus paste that guy down there, and got to tell it to do atmospheres, or it's going to convert it to pascals. 5.3625. So that's equal to 5.3625 atmospheres. That's the net osmotic pressure. Notice that since we only had a quarter of the solute in there, in the saline, the concentration of it has gone down. The pressure here versus the pressure here, we're at much less pressure than we should be. So blood should really be pushing and backing up our IV, which isn't good. Let's look at the next problem. Here they say the diameter of a typical red blood cell is 5.98 micrometers. That's 10 to the negative 6. We want to calculate the net force of the solution on that the solution experiences across the membrane, assuming that the red blood cell is a sphere. So we're simplifying the solution. I think I've always seen blood cells depicted as kind of a weird torus or disc with those round edges, but we're going to simplify it, call it a sphere. Makes it a lot easier to calculate. So some of the things that we know the diameter of the red blood cell, right? We said the diameter is equal to 5.98 micrometers. And we're saying that and that's equal to 5.98 times 10 to the negative 6. If you haven't memorized all of your metric unit conversions, micro, milli, let's go the right way. Milli is 10 to the negative 3, micro is 10 to the negative 6, nano is 10 to the negative 9, pico is 10 to the negative 12, and after that you're getting subatomic, so even by pico you're getting subatomic. So you probably don't have to worry about that for a while. It's a good thing to memorize because it's an easy mistake to make. And we said our net osmotic pressure, and they're converting it to pascals, 5.363. That's atmospheres. So we can convert that 1 atmosphere divided by 1.01300 pascals per atmosphere. And we can, well, my calculator will just do that if I just do this. So that would be 543,355 pascals. 543,355. 543,355 pascals. And we want to find the change in force, right? We want to find the force that's being exerted on those red blood cells. So, I guess the sum of forces, not the change, the total forces. So we can we can calculate that by saying it's the change in pressure times the area, right? Because pressure is equal to force per area. So if we multiply it by the area, we'll end up getting the force per area on there. So that's going to be equal to our osmotic pressure, the net osmotic pressure, times the area of the red blood cell. I'll say blood, the area of the blood cell. So now we know the diameter of that red blood cell is this, so the radius is going to be half of that. So we can just divide that by 2. That's 5.98 times 10 to the negative 6 meters, all divided by 2. And that would be 2.99 10 to the 6. So about 3. So we can say the radius of blood equals 2.99 times 10 to the negative 6 meters. Now our surface area of a sphere, right? So we need to know what that surface area of that blood is. So to find that, we have to find the surface area of the sphere and take the pressure and divide or multiply by that area. So that surface area of the sphere is 4 pi r squared, which is equal then to 4 pi times 2.199 times 2.99 times 10 to the negative 6 meters squared. So that squared times pi times 4 excuse me, is going to be equal to our surface area. So that's 1.12345. Wow, that's unusual. Times 10 to the negative 10 meters squared. I'm going to say 1.1, was it 1.12345? Yep. 2345 times 10 to the negative 10 meters squared. That's the surface area of the red blood cell. So now we can just say that the summation of forces is going to be equal to the net osmotic pressure in pascals, which is 54335 pascals. And we need to multiply that by 1.12345 times 10 to the negative 10 meters squared. The reason we had to convert to pascals is the units of newtons per meter squared. If we left it in atmospheres, our answer would be incorrect at the end because their units would be off. So taking our pascals, multiplying it by our area, I'm getting 6.1404 times 10 to the negative 5 newtons. This is equal to 6.103 times 10 to the negative 5 newtons. So you can see, even though we have about 7 atmospheres of osmotic pressure in our blood cells, the actual force that's actually be doing force per square inch or square meter is actually 6.104 times 10 to the negative 5 newtons. So it's pretty small in order of magnitude, but our blood vessels are pretty small too. So we can ask ourselves now, how tall of a column of mercury would the net osmotic pressure from part B support, considering that the density of the liquid mercury at STP is 13,534 kilometers per meter squared. So we can use the net osmotic pressure that we had, which is equal to 5.432 times 10 to the 5 pascals, and the density of mercury, so that's the density of Hg, which is equal to 13,534 kilograms per meters cubed, and gravity, which is equal to 9.8 meters per second squared. Now, we can use the basic idea that the change in pressure would be equal to the density times gravity times the change in height, which in this case, plugging in some of these values, we have the density. I guess we want to know the change in height, so we want to solve for height. So solving that equation for height, delta H is going to be equal to delta P over rho G. So now plugging in some of those values we can say that the change in pressure is really the osmotic pressure difference, the net osmotic pressure. So that's 5.432 times 10 to the 5 pascals. I'm going to divide that by the density of mercury, 34 kilograms per meters cubed, and then multiply that by gravity, 9.8 meters per second squared. And we can, let's do that and solve for the height. So I'm just going to go up and grab my value for pascals. And I need to divide that by 13,534. That's kilograms per meters cubed. And also by gravity, which is 9.8 meters per second squared. And we get 4.097 meters. This is equal to 4.097 meters. So that's how high up the Mercury column would be at that pressure. Okay, so we have another one here. Here we're going to talk about a diver who goes down to 224 feet below sea level and stays there for some time. What is the absolute pressure that they experience at this depth? Now again, pressure is going to be equal to the density times gravity times delta H. Oops, the change in pressure. I just wrote a triangle. There we are. Now, we know the pressure at the atmosphere, or pressure at the surface, is equal to 1 atmosphere, which is equal to 101,300 pascals. And we know that the density of water, because that's what he's diving down in, is going to be equal to 1,000 kilograms per meters cubed. And delta H is equal to, we said 224 feet. So we want to convert that to meters, so we can multiply this by 0.3048 meters per foot. Let's see what we get there. Just because we want to make sure we cancel out the feet and get to meters. So 224 feet times 0.3048 meters per foot. Give me 68.28 meters. And then gravity, of course, is equal to 9.8. So now we have the values we need for there, and we just have to solve for the pressure in the depth. So remember, the change in pressure is always equal to final minus initial. So the pressure of the diver, let's say diver, minus the pressure at the surface will be equal to this. Let's move it down. I'm going to run out of space if I don't. To the density of gravity, which is 1,000 kilograms per meters cubed, times gravity at 9.8 meters per second squared, times the change in height, which we said was 68.28 meters, And all right, let's plug that in. So it was 1,000 kilograms per meters cubed times 9.8 meters per second squared times 68.28 meters. Oh, what I forgot to do. What did I forget to do? So that's this equal to the change in pressure. But we need to subtract from that, or add from that, to both sides to cancel that. So the change in pressure, or the pressure at the surface, is 1 atmosphere, so that's 1,001,300 pascals. So taking the answer we just got and adding to that 101,300 pascals, now we get 707,444 pascals. So the pressure of the diver is equal to 770,444 pascals. So that's the pressure that they're at when they're 224 feet below the surface. So as the diver begins to ascend and go up higher in the surface, a small bubble of nitrogen, a diameter of 1.8 micrometers, comes out of the solution into his bloodstream. We want to find that diameter at the surface. So to do this, we need to look at use the ideal gas law, or which is really PV is equal to nRT. Since we're having a few things stay relatively constant, we can use this as the change in pressure versus volume. So we can say P1 V1 is equal to P2 V2. So we really want to know how much that volume has expanded. Now we have already said that the diameter of this is equal to 1.8 times 10 to the negative 6 meters. That's micrometers. The pressure at the surface is 1 atmosphere, which is 101,300 pascals. And the pressure at the depth of the diver is equal, what did I say, 770,444 pascals. So now we can just solve for the volume at the surface. And first we actually need to find the volume down below. We know the diameter, but the volume of a sphere is going to be equal to, was it 4/3 pi r cubed? So using the diameter they give us to find the radius, to find the volume, I can say this is 4/3 pi times 1.8 times 10 to the negative 6 divided by 2. These brackets go all the way down so I can cube it. And let's find out what that is real quick. So that's 4/3 pi times 1.8 times 10 to the negative 6 meters. And we're going to cube it. Oh, first we got to divide it by 2. There we are. So the volume of that sphere down below is going to equal this 5.35358 times 10 to the negative 17 cubic meters. Let me look at this. 5.358. 5.358 times 10 to the negative 17 cubic meters. So plugging that value into for V1, we can then solve for V2 because we know the pressure at both depths. So P1 is the pressure at the diver, and the V1 is the volume that we just calculated. So that's going to be 770,444 pascals times the volume 5.358 times 10 to the negative 17 cubic meters. And then we're going to divide that by the pressure at the surface. So that's just atmospheric pressure, 101,300 pascals. And that should equal whatever the volume that this N2 gas has expanded. So here's my 770,444 pascals. We're going to multiply that by, that's the volume down at the depth of 224 feet. We're going to divide that value now by 1 atmosphere to save a little bit of time because we're almost out of time. And this gives us 4.074 times 10 to the negative 16 cubic meters. 4.074 times 10 to the negative 16. 4.074 times 10 to the negative 16 meters. So we want to know the diameter of it. So we can, again, now using that same pi r cubed, this is, this should be cubic. That's equal to that volume. So that's equal to 4.074 times 10 to the negative 16 meters cubed. Just to solve for that radius real quick, I can say that R is going to be equal to 3/4 times 4.074 times 10 to the negative 16 meters cubed. And then I'm going to divide by pi. Take that whole thing. I need to do the cubed root to get r by itself, so I'll take that whole thing to the 1/3 power. And that should give us our radius. 3/4 times that divided by pi, all to the 1/3 power. And that's 4.598 times 10 to the negative 6. That's in meters. So notice it went from 1.8 micrometers to 4.6 micrometers. So it's gotten quite a bit bigger, but still not really big enough to cause any trouble. That's all the time we have this time. Definitely fill out the attendance sheet if you haven't already. Oops. Let me paste it back in there. Also, stop into my drop-in hours just after this, or make an appointment with another tutor on Penji. Again, my name is Travis, and have a wonderful day and best of luck.